We have spoken about general regulation of enzymes, but now we're going to look at specific regulation of different types of allosteric regulation, both activators and inhibitors of different enzymes in glycolysis and gluconeogenesis. In this pathway, there are actually two primary sites of regulation. When we're looking at the conversion of pyruvate and phosphoenol pyruvate, and then also the conversion of fructose 1,6 bisphosphate to fructose 6-phosphate and vice versa. So you can see that inhibitors here have the lines with the kind of line at the end, and activators are actually going to have the arrow at the end. So you can see this positive arrow. That's an activator of phosphofructokinase 1, for example, this fructose 2,6 bisphosphate. I'm going to zoom in and talk a little more specifically about just one of these, that step on the top end of, the bottom end of the glycolysis pathway when we're looking at making pyruvate. Now, you can see here that if we have pyruvate, we're going back up to oxaloacetate and making phosphoenol pyruvate. Acetyl-CoA is actually a positive activator, an allosteric activator of pyruvate carboxylase. This kind of makes sense if you think about it. Acetyl-CoA, remember, is a downstream product of, this is kind of pyruvate, and then we go to acetyl-CoA, which gets transferred to acetyl-CoA in the mitochondria. And that means when we have a lot of this acetyl-CoA, that means we have a lot of product down here. And it also means that we have a lot of energy, and we have a lot of the product here. If we have a lot of product of glycolysis, that means that we might want to actually go back up this way to actually activate the synthesis of oxaloacetate, phosphoenol, pyruvate to actually undergo gluconeogenesis. So again, when we have a lot of acetyl-CoA, that activates the gluconeogenesis pathway. On the other end of things, if we have a lot of fructose 1,6 bisphosphate, that is actually a reactant upstream of glycolysis. So we're actually going to here, if we activate the pyruvate kinase, we're actually going to activate glycolysis as well. So again, if we have reactants in that glycolysis pathway, we're going to activate one pathway, versus if we have products of the glycolysis pathway, we actually might want to go and activate the reverse reaction. Now, if we look at these inhibitors, ATP and phosphorylation, let's start at ATP. If we actually zoom out back to this earlier diagram, you can see fructose 1,6 bisphosphate is up here. It's on this, right after this irreversible step. So if we have a lot of this reactant here, that can actually activate the this pathway. Actually acts as a activator of pyruvate kinase, so we can get rid of some of this reactant. So it's a good way of upstream activator of this pathway, so we can make more pyruvate. And now let's look at ATP here. So if we have ATP, it actually can act as an inhibitor of the pyruvate kinase. And that makes sense to some extent. Glycolysis, the point of glycolysis is to make ATP. And if we have a lot of it already, then that process can slow the glycolysis down, since we don't need more ATP, and potentially that can allow us to build up glucose and use that for other processes. For example, like making glycogen stores. And we'll come back to this protein kinase A in a little bit. This can also act as an inhibitor to pyruvate kinase. I just wanted to show you also some of the interactivity, the cooperativity of some of these enzymes and what they look like. And this is actually the BCC shown here in red on the left side of this image. And we're going to look at some of these enzymes. And this is actually the biotin carboxycarrier protein, or BCC. You can see it kind of fits in here on the pyruvate carboxylase here is also shown, and then there's this cooperative binding that this actually fits into. We have the CoA here, we have ATP. So if we go back to this pyruvate carboxylase, actually we can see the binding to that BCCP protein, and that's again shown here. This is kind of the three-dimensional image of that. So we can have this cooperative binding of these different subunits, and they can influence each other and change the affinity, change the shape of these enzymes, and act as either cooperative or inhibitive binding. Here's the other location of one of those irreversible steps where there's high regulation. So this is the other site of primary regulation for glycolysis and gluconeogenesis. And you'll see that one of those things that we're looking at here, both AMP and fructose 2,6 bisphosphate have opposing regulatory functions. So when there's high levels of AMP, less energetic form of adenosine, that's adenosine monophosphate instead of triphosphate. Remember, the kind of point of glucose being broken down in glycolysis is to make more ATP for our body. So if there's high levels of AMP, that means we probably have low ATP reserves. AMP is going to actually inhibit and reduce the buildup of glucose, and it's going to actually activate the breakdown of glucose. So that kind of makes sense, right? We need more ATP, less AMP, so we're going to slow down this process. We're going to break it down and hopefully make some more AMP. So we have activation of this phosphofructokinase be activated by AMP, and then the fructose 1,6 bisphosphatase, which is going backwards in gluconeogenesis, should be inhibited. The same kind of idea where the fructose 2,6 bisphosphate here is inhibiting this, and actually on this side is going to be activating this. These are both kind of ways that we can change that if this is going to be going down to glycolysis or going up to gluconeogenesis, and this regulatory mechanism kind of doubly activated here. Likewise, if there's a lot of ATP, this can also inhibit this phosphofructokinase. And citrate just kind of tells us that if we have high levels of citrate, it kind of tells us we have high energy levels. And we have lots of components for the citric acid cycle, for example, to work with, and we don't necessarily need any more. Again, some major sites of regulation here for these different enzymes. Looking just a bit closer at the protein and the protein structure here, AMP actually acts as an allosteric inhibitor, and as fructose 2,6 bisphosphate acts as a competitive inhibitor. So this is for the tight form, the inactive form of 1,6 bisphosphatase, and it's actually bound to different compounds of AMP here that's acting as an allosteric inhibitor. You can see it's trimeric, so there's 1, 2, 3, 4, actual 4 components of this. And again, this is where this is the inhibitor, and this is the enzyme, the fructose 1,6 bisphosphatase that we're actually looking at over here. So the more AMP that is there, the higher the concentration, right? The more that can be bound in these different regions, and then the less active this enzyme gets. So based on this information above, what does this say about where these two factors are binding fructose 1,6 bisphosphatase? So if AMP acts as an allosteric inhibitor versus fructose 2,6 bisphosphate acts as a competitive inhibitor. So are they binding in the same domain, in a different region? Remember, go back to some of the last chapters about enzymes and enzyme kinetics. Think about what that means for the active site and where, either of these you think that they bind, if it's in that active site or not. I'm not going to give you the answer right now, but if you have a question on this, come and see me in my office hours.